I don't know.
I'm not going to give a long introduction on how much I owe to Howard, because this whole paper is a discussion of, well, how I came to understand, I think, the yes but paper, and defending it as the best possible solution to the instrumentalism realism issue. Methodological, and the answer is methodological structuralism. Methodological structuralism is an alternative to both contemporary structural realism and to more instrumentalist versions of structuralism, such as that defended arguably by Rudolf Carnap in his Ramsey sentence reconstruction of scientific theories. My argument owes much to two contemporary philosophical scholars of the development of modern physics. See if you can guess who the two people are. Beginning with Newton and extending through the late 19th and early 20th century, Howard Stein and George Smith. From the former, Howard, I take the conception of abstract structures in the phenomena. From the latter, George, a conception of theory-mediated measurement. Putting these two conceptions together is my way, in particular, of finally beginning to understand, I hope, and of course, thinking Howard was here, I knew I had to say, I hope, what Howard has been saying about this issue all along. I think I've got it. I begin with a well-known, or maybe not so well-known, meeting of the 8th International Colloquium of the Institut de la Méthode, taking place in Neuchâtel, Switzerland, May 26, 29, 1988. The papers from which then appear in Dialectic in 1989. I realized later, because I've asked various people if they knew who was at this conference, or even knew what the conference was, and I realized that many of you just go to JSTOR, you don't look at journal issues, and you just download the thing you want, which was Howard's paper. So what's interesting here is that if you look at who was there, it was Worrell, when he first gave his argument about structural realism, and Howard is there too. And it's interesting, if you look there, you see that Worrell, in his footnote to the written version of the paper, of the talk, says that he gives his debts to various people, but the only person who was at the conference who he thanks is Howard. The subject of the meeting was realism today, and it involved an impressive cast of contemporary philosophers of the time, most, if not quite all, philosophers of science. The meeting and the resulting volume were notable, among other things, for marking the beginning of the modern discussion of structural realism within philosophy of science. A discussion that continues today with unabated enthusiasm, if not with comparable clarity and insight. And the paper that sparked this modern discussion was, of course, Worrell's Structural Realism, the Best of Both Worlds, question mark. Maybe the question mark was inspired by Howard, as well as Worrell's very qualified attitude toward the no miracles argument, but I don't know. For Worrell, the two worlds in question are realism and anti-realism, and Worrell attempted to do justice to both, if only somewhat tentatively, by reviving what he took to be an earlier version of structural realism articulated by Henri Poincaré. Worrell's idea, in brief, was to find sufficient continuity in scientific change to support the legitimate claims of scientific realism, while simultaneously acknowledging that the reference of central theoretical terms may radically change in the process or even disappear altogether. His main example involved the mechanical models of the luminiferous and electromagnetic ether that were explored throughout the 19th century, which it is supposed were later found to have no physical reality after all, especially after Einsteinian relativity theory. Of course, Howard didn't think that. Worrell's contention, in a nutshell, is that although these ethers themselves, conceived as material substances, were not preserved over time, the mathematical structures involved in their description, waveforms continuously propagating over space and time, electromagnetic lines of force, vector fields in the theories of Faraday and Maxwell, were preserved nonetheless. It is here, for Worrell, that we find the invariant mathematical structures that remain after the appearance of their originally supposed material content. But the paper that is most interest to us, of course, is Howard Stein's Yes, But, some skeptical remarks on realism and anti-realism, which we've had a fair amount of discussion already today and yesterday. Here, without referring to Worrell's paper, mostly he takes Boyd as his target, Stein embarks on an analogous project of reconciliation between two attitudes towards scientific theories that are standardly taken to be diametrically opposed to another. This time, realism and instrumentalism, not anti-realism. That Howard doesn't like. Stein argues, on the contrary, that realism and instrumentalism are fruitfully combined with one another in the work of the greatest scientists, and in particular in the work of Newton, Maxwell, and Einstein. Realism, insofar as their goal is adequately and correctly to represent the phenomena of nature, but instrumentalism also, insofar as their project can only proceed by very careful attention to the empirical evidence by which we take a given theory adequately and correctly to represent the phenomena. We must be able to find the theoretical structures in question in the phenomena themselves, in something like the way, Howard says, in which we find enduring physical objects in our everyday sensory experience. Actually, that last thing, I think, is maybe the only thing that I don't agree with. Now, this talk of representing the phenomena and of finding theoretical structures in the phenomena may appear unsatisfactory from a realist point of view. For one of the key moments in the development of modern science, Galileo's refusal to take up Cardinal Bellarmine's invitation, more than an invitation, to confine Copernican theory to the goal of saving the phenomena, this appears to have involved precisely a realist commitment on Galileo's part, going well beyond the goal of saving the phenomena. And a similar dialectic, of course, appears to be present in later collisions between realism and instrumentalism, such as Duhem's rejection of contemporaneous molecular atomic theories, again on behalf of saving the phenomena, and in our own time, in the related defense of instrumentalism, explicitly as opposed to realism, by Bas van Fraassen. I confess that I was not quite satisfied with Howard's position along precisely these lines for a considerable period of time, especially in my earlier, now long ago, militantly realist phase. Moreover, I continued to have trouble understanding Howard's position, even as I grew ever more confident. In the Dialectica essay, you may recall, Howard invokes the Kantian critique of transcendental metaphysics on behalf of the view that, quote, all theoretical of knowledge is of the phenomenal world, the world of experience, in just Kant's sense. I think that I have now found the source of my misunderstanding of Howard, and it is interestingly connected with a second misunderstanding of an apparent criticism of Newton articulated by Kant. The apparent criticism by Kant appears in the second remark to Proposition 7 of the Dynamics chapter of Kant's Metaphysical Foundations of Natural Science. I assure you this whole paper is not going to be about that.
But it could be.
It very easily could. That's why I have to be careful. Where Kant appears sharply to differ with Newton concerning gravity as an immediate action at a distance. Well, the difference seems to be in the first sentence. Newton was set at variance with himself, he's saying, if he had any qualms about action at a distance. And the point is that what is at issue is the method Newton develops in Book 3 of the Principia for measuring the masses of primary bodies by the accelerations produced in their satellites. Here is exemplified by Jupiter and Saturn. A method that is paradigmatic for me of what George Smith calls theory-mediated measurement. Newton, according to Kant, must assume the immediacy of the gravitational interaction between Jupiter and Saturn, independently of any intervening matter surrounding them, in order to infer their masses from the accelerations of their moons. This is connected to the Coates issue and what George was talking about. And then briefly, if we begin with the acceleration field of gravitation, that all bodies fall the same in a gravitational field, where this constant k is a different thing for each body. Here, the body A, the primary body. The question is, what do you say about the mass of A? And the argument for that in the case of Jupiter and Saturn looks something like this. Each one has an acceleration field. That's, of course, Howard's notion as well, satisfying this proportionality. And how do we get that connected to mass? Well, if you bring in the immediacy and the universality of gravitational interaction, so that Saturn and Jupiter must attract each other as well, and then you apply the action and reaction to that very thing, then you get, by this very simple argument, that the accelerations are proportional to the masses of the primary bodies. And of course, George has rightly emphasized that there was no direct evidence for this. The point here is that this is an important part of Newton's argument in Book 3, as Coach rightly observed. Is Kant saying, however, that Newton must accept the existence of real action at a distance, despite the qualms vigorously expressed by contemporary representatives of the mechanical philosophy, such as Huygens and Leibniz? This is what I had thought. This question is more subtle than I had previously thought, as many questions are. For consider what Kant says right before the quoted passage. Kant says, Newton rightly abstracted from all hypotheses purporting to answer the question as to the cause of universal attraction of matter. For this question is physical or metaphysical, but not mathematical. Here Kant seems to be, and I think is, endorsing the abstract treatment of impressed force as a measurable mathematical quantity that Newton had been articulating since Proposition 1 of Book 1, which demonstrates that Kepler's area law for a given trajectory is mathematically equivalent to generation by a centripetal force always directed toward the center S, whatever its deeper explanation might be. So we don't need to know what it is that's causing that motion, that deviation from inertiality at B, C, D, E, and F, as long as there is something producing that. The aim is to determine the mathematical properties of this force, here having to do with the area law. That is, the area law follows from the fact that you have a centripetal force, or any centripetal force. These properties to support inferences from empirical, albeit mathematically expressed propositions, like Kepler's rules, to further mathematical properties of the force in question, such as the inverse square law for gravitational force. We thereby open the way to a continued series of empirical inferences that progressively correct the mathematical laws obtained at one stage by considering ever more subtle effects of gravitational force, which both further support the earlier obtained laws, while also revealing their fundamentally approximate character. Well, this is familiar from Howard and from George. Thus, for example, Newton's derivation from phenomena 6 in Proposition 3 of Book 3 of an inverse square acceleration of the moon towards the Earth involves a promissory note already in the first thing, qualifying this concerning the perturbative effect of the sun on the moon. But the note only begins to be redeemed later in Book 3, and down here he qualifies it even more precisely. He gives a calculation showing that the exponent of the acceleration toward the Earth is not quite 2, or it's a little bit bigger than 2. And he says this motion of the apogee arises from the action of the sun, as will be pointed out below, that is later in Book 3 with the three-body problem, and accordingly we can ignore it here while also acknowledging that it's there. So it has to be explained. The note only begins to be redeemed much later in Book 3 with Newton's detailed attack on the three-body problem, and it is only fully redeemed after Newton's death by Euler's and Clairaut's first successful treatment of the motion of the moon in the 1740s. A similar sequence of increasingly accurate approximations leads, as already suggested, from Kepler's rules, assuming them exact, to corrections of them based on the perturbative effects of bodies other than the sun, and so on. This procedure of approximative correction and theory-made measurement, here of the relevant accelerations, continues with ever-increasing success throughout the 19th century. The most spectacular being the well-known discovery of Neptune by Adams and Leverrier in 1846. Decisive obstacles arose only at the turn of the 20th century, when minute deviations in the predicted advance of the perihelion of Mercury eluded all attempts at solutions with the Newtonian theory. This is, of course, familiar to all of us. The first successful solution then became one of the triumphs of Einstein's general theory of relativity, a fundamentally revised theory of gravitation in 1915. I shall return to that below. Meanwhile, what is the evidence, however, for attributing the Newtonian conception of impressed force, which abstracts from all hypotheses concerning the underlying mechanism of gravitational interaction? What is the evidence for attributing that to Kant? Well, there is more evidence than I can review here, and I don't think you want to hear it. But it is clear in any case that Kant was familiar with Newton's hypothesis non-fingo passage in the general Scholium to the Principia, which of course we know and we've seen already. I have not yet been able to deduce from phenomena the reason for these properties of gravity, and I do not feign hypothesis. For whatever is not deduced from the phenomena must be called a hypothesis, and hypotheses, whether physical or metaphysical, or based on occult qualities or mechanical, have no place in experimental philosophy. Newton is here defending his mathematical law of gravitation from criticisms raised by mechanical philosophers, especially Huygens and Leibniz, especially Huygens, who insisted on the priority of action by contact in order to explain this law. And Kant develops a parallel response to the mechanical philosophy on the behalf of what he calls a metaphysical dynamical mode of explanation in the general remark to dynamics, and he uses the German word for feigning, which is erdichten, to make the point. Moreover, what Kant says about the question in his second remark to proposition 2, which we already looked at, seems to be echoing Newton and be quite consistent with what Newton says in the hypothesis non-fingo passage, but I won't go into any more detail. But let me summarize and clarify the relationship, as I now see it, between Newton's conception of force and Kant's. The first point is that Kant accepts Newton's abstract conception of force as a measurable mathematical magnitude considered independently of all merely hypothetical elements. This does not mean that force is either what we would call an abstract mathematical entity or what we would call an observable as opposed to theoretical entity, one reducible to purely observational theory-neutral concepts. On the contrary, the fundamental concepts of mass, force, and acceleration function as primitive terms, what we would call primitive terms in Newton's physical theory, where they are related to one another mathematically and are thereby articulated mathematically, and also, as we'll see, empirically, via Newton's axioms or laws of motion. The latter, and this is the second point, serve to enable theory-mediated measurements of these quantities, including the quantity of duration, elapsed time. Thus, for example, given the observed Keplerian orbits, Proposition 1 of Book 1 provides an empirical measure of duration in terms of geometrical errors. Later propositions of the Principia provide an empirical inverse square estimation of the centripetal force in question. And as we have seen, still later propositions successfully build on these results to provide a universal common measure of mass or quantity of matter for the primary bodies of the solar system. When we speak, following Howard, of abstract structures in the phenomena, we are not endorsing contemporary structural realism, as defended by Rawle and his followers. Rather, we are referring to systems of empirically determinable law-like relations between empirically measurable, albeit still theoretical quantities, theoretical in the sense that their meaning is articulated by the axioms or laws of motion foundational to Newton's theory, and I mean mass, force, and acceleration. The resulting system of empirically determinable theoretical relations are to be contrasted with the merely hypothetical postulation of the theoretical entities that may not have, at least at present, any such means of empirical determination. Thus, for example, while contemporary representatives, contemporary to Newton, of the mechanical philosophy insisted on the need for vortex models of planetary motion to explain Newton's results, he, Newton, was well within his rights to reject this insistence on behalf of his so far not further explained law of universal gravitation, which is well empirically determined, since the vortical motions, by contrast, lacked all means at the time of robust empirical determination. What is most important, following George, is that the possibility of robust empirical determinations of the relevant physical quantities via theory-mediated measurements provides Newton's theory with a more secure epistemic status than either mere inductive inferences, curve fitting, or mere hypothetico-deductive arguments, that is, inference to the best explanation. The relative weakness of mere hypothetico-deductive arguments is well illustrated by the example of Newton's confrontation with the mechanical philosophy over its insistence on vortex models of planetary motion. For the relative weakness of mere inductive inferences, on the other hand, consider the relationship between Newton's argument for the law of gravitation and Kepler's so far merely inductive rules. They're actually not merely inductive. They're a more careful story about Kepler, but I'll skip over that. To be sure, Newton begins his argument from the observable Keplerian phenomena, taken provisionally as well-supported universal claims. The crucial point, however, is that Newton's argument involves an open-ended sequence of corrections to Kepler's rules, taking increasingly accurate account of gravitational perturbations. Indeed, these corrections lead to the conclusion that the orbits in question are not even closed curves due to perturbatively induced precession, a conclusion that could not be effectively reached by the collection of further data points and curve fitting. It is precisely here, in my view, that the greater strength of the characteristically Newtonian method of reasoning from phenomena becomes fully clear. And with respect to this issue of realism versus saving the phenomena in particular, it turns out that Newton could thereby settle the issue between Galileo and Bellarmine empirically by theory-mated measurements of the masses of the primary bodies in the solar system. As we know, the center of mass of this system, which is always very close to the center of the sun, is the preferred dynamical center of motions in Newton's sense of dynamical center, whereas a merely theoretical description, by contrast, necessarily involves an otherwise arbitrary choice of reference frame. This Newtonian methodological empirical solution to the structure of the solar system, via appropriate theory-mated measurements to the classical astronomical problem of realism versus saving the phenomena, generalizes to other similar cases. So the crucial point is, saving the phenomena in the sense of the classical astronomical tradition is not the same as what Howard means finding a structure in the phenomena at all, because for that you use theoretical relations which are still empirically determinable about forces. And this very same kind of argument can be generalized to other similar cases of classical realism instrumentalism. And in particular, Perrin's resolution of the problem of molecular reality via precise microscopic measurements of the motion of Brownian particles. Here, see the recent detailed work on this case by George Smith and also William Dimopoulos. This, in the end, is why Howard's conception, as I already said, of abstract structures in the phenomena is not vulnerable to the charge of instrumentalism in the Bellarmine, Duhem, von Fraussen senses. On the contrary, I say, Howard's view provides the strongest possible rebuttal to that instrumentalist line of thought by showing that as physics develops, it then becomes a problem of physics, not of metaphysics, to settle the question, which then can be settled empirically. And then the last point, this greater epistemic strength in my reading is a centrally important constituent of Kant's, as well as Newton's, purely epistemic, that is Kant's notion of causal necessity. This is something that George and I kind of came to together after he spent a year at Stanford, and I sat in on his Newton course for the nth time, and he sat on for the first time to one of my Kant courses, but we both came away with, yeah, Kant's causal necessity should be understood in terms of this Newtonian. Now, the original Newtonian method of reasoning, based on his formulation of the laws of motion, breaks down, as I suggested, and as we know, in the case of minute deviations from the predicted perturbations of the orbit of Mercury, which are only adequately explained on the basis of Einstein's theory of relativity developed in the years 1905 and 1915. And of course, we should remember that various other people, like Poincaré and others, had their own ways of trying to explain it, but they never could get the full value. Only Einstein did that. At the end of this development, our conception of gravitation takes a completely unexpected direction by now considering a non-Newtonian causal action exerted by the variable non-Euclidean curvature of space-time. And it is at precisely this point that the original Kantian conception of force and causal necessity also breaks down. While Kant does have room for the corrections to the planetary orbits that can be accounted for within the Newtonian theory of gravitation, that is, the Newtonian gravitational perturbations, here you see the one place I have found in Kant in the first critique where he explicitly acknowledges the importance of these perturbations. First you have circular orbits, then elliptical orbits, and then you have, in this little passage, above this passage, well, he mentions them here, eventually hyperbolic orbits, although there's no evidence for any of those at the time. But from there, we get to the law of their motion of gravitation, and once we have that law, that is a law of a force, we can extend our conquests further, seeking also to explain all variations and apparent deviations from these rules using these conic sections from this very same principle that is gravitation. Okay, so Kant had room for that, bravo Kant, but Kant has no room for causal actions exerted by a non-Euclidean variation of curvature in our form of outer spatial intuition. You can't do that for Kant. So I shall leave aside further discussion of Kant at this point, you might be relieved, to consider how the original Newtonian method of reasoning from phenomena becomes generalized to post-Newtonian and post-Kantian physics. I shall approach this question as before, and now I'm going to get to Howard's other heroes in the story, by focusing on the concept of force, and more generally the concept of interaction. Einstein's general theory of relativity, of course, is, like Newton's theory, a theory of specifically gravitational interaction. In order to properly appreciate Einstein's theory, however, that is general relativity, we must first gain an appreciation of Einstein's earlier 1905 special theory of relativity, which articulates a post-Newtonian spatio-temporal framework for considering electromagnetic force. The second of what we now take to be the four fundamental forces of nature, beginning in order of discovery with gravitational force. Now, we think an adequate and correct representation of what we now call the electromagnetic field was achieved by Maxwell in the second half of the late 19th century. Second half of the 19th century, not the second. In terms of, as we now understand it, of electric and magnetic force vectors here in a wave, continuously distributed over space. This field of force, like Newtonian gravitational force, is a mathematically described physical magnitude. And as such, it can be studied in abstraction from, independently of, any deeper physical realization aside from the field itself. Involving, for example, underlying motions in mechanical ethers, such as, for example, an elastic ether. Unlike gravitational force, however, the electromagnetic field is itself dynamical. It is continuously propagated through space with a definite finite velocity c, the velocity of light. It is thus, as Howard has observed in the 1970 paper on the notion of field in Newton, Maxwell, and beyond, it is an actor in the physical world along with the matter upon which it acts. This isn't true of Newtonian gravitation. There are energy and momentum exchanges between matter and the field, for example, not only among the material bodies themselves. And of course, light waves on Maxwell's theory are propagations in the electromagnetic field confined to wavelengths within the visible spectrum. And the electromagnetic spectrum, of course, extends beyond visible light on both ends, with successively shorter wavelengths, as in ultraviolet, X-rays, and gamma rays, and successively longer wavelengths, as in infrared, radio, and now microwaves, the most important of all. Otherwise, we couldn't have cell phones. But how do we know that this Maxwellian representation of the electromagnetic field is adequate and correct? Of course, we take this for granted. Heinrich Hertz's celebrated experiments toward the end of the 19th century involved the first generation and reception of electromagnetic waves by means of what we might now conceive as a radio transmitter and receiver of sorts located several meters apart. Hertz could thereby measure the velocity of transmission, which turned out, as predicted, to be the same as the velocity of light, and compare the frequencies of oscillations in the transmitter and antenna receiver, which turned out as predicted to be the same. Otherwise, you couldn't have a very good radio, could you? Perhaps most importantly, as Stein observed also in that 1970 paper, Hertz thereby effected an empirical realization and clarification of the characteristically Maxwellian displacement current, and thereby empirically distinguished Maxwell's theory of electromagnetism from its 19th century competitors. On the one hand, the Weberian action at a distance theory, where we view the force, all electromagnetic forces to be reducible to forces between elementary electric charges acting only in relation to distance, and the Helmholtzian theory of an interaction potential between macroscopic charge and current distributions. Hertz's experiments, and it turns out, and if you look, say, at Jed Buchwald's very, very detailed discussion, the point is that these other theories, contrary to Hertz's original anticipation of what he wanted to find, stand apart from Maxwell's theory. You can't get Maxwell's theory from them, because from them you can't get wave propagation or any of these continuous propagations over space that you get from Maxwell. Hertz's experiments in this sense empirically realized the Maxwellian electromagnetic field and established its mathematical properties, just as those of gravitational force had been established 2 centuries earlier by Newton's inferences from phenomena. Now, in the case of this kind of example, I feel like saying that if we want to talk about the schematism here, what it is the theory has to be schematized, say Maxwell's theory, his equations. They need to be schematized, that is, realized in empirical experiments if they're going to be the subject of empirical. It's not so much the observer that needs to be schematized, but the theory, the abstract theory does. At least that's an important aspect of it. In both cases, however, I said these, just as those of gravitational force have been established, both have been established, one by Hertz, the other by Newton. In both cases, however, established does not mean by any means proved to be correct with no possibility of revision. That would be crazy. Rather, Newton's inferences from phenomena and Hertz's experiments provided the corresponding forces with observational, determinable empirical reality. That is, it schematized them and showed that, at least to a first approximation, they are the correct, as far as we know, given their competitors' correct representations. They thereby, these experiments and observations, established the possibility of continuing progressive empirical inquiry into the respective forces, gravity, electromagnetism, a process which, as we saw, is always open to further correction as our empirical determinations of the relevant quantities become increasingly precise. This kind of reasoning provides such empirical determinations with greater epistemic security than either merely inductive reasoning or hypothetical deductive reasoning. That's again the point. Thus, just as in the case of Newton and the mechanical philosophy, the hypothetical ether models that were originally proposed for both the wave theory of light and electromagnetic theory were considerably more problematic than Hertz's experimental investigations into the mathematical properties of the Maxwellian electromagnetic field, which could thus be empirically and mathematically investigated independently of any such model. Just like you could go ahead and investigate gravitational force without a vortex model which just gets in your way. We can now appreciate how Einstein's general theory of relativity is bound up with his special theory by showing that there is a fundamental tension between the kind of causality exemplified by the Maxwellian electromagnetic field and that of Newtonian universal gravitation. This is well known to all of us. The latter, Newtonian gravitation, is propagated instantaneously along planes of absolute simultaneity, as we now call them. It's always in the Newtonian spatio-temporal background structure, which contains these planes. While the former, the Maxwell field, is always propagated with finite velocity c. But no finite velocity can be the same in two different inertial frames of reference in a Newtonian spatio-temporal structure. That's what this little picture is supposed to show. Only the planes of absolute simultaneity themselves, representing infinitely fast or instantaneous causal actions, are invariant in such a structure, a Newtonian structure. The special theory of relativity then addressed this tension by changing the spatio-temporal background to what we now call, of course, Minkowski spacetime, wherein the symmetries of Maxwellian finitely propagated causality are taken to be also the symmetries of the spatio-temporal background structure as well. So it's not as it were there are Galilean symmetries put together with Maxwellian symmetries to leave just a group that has no motions in it. In particular, the simultaneity relation in special relativity is relativized, as we know, so that there are different planes of simultaneity through a given point event relative to different inertial frames. The light cone determined by all spatio-temporal trajectories with a given finite velocity c through a given point event now replaces the plane of absolute simultaneity through this point as fundamental spatial temporal invariant. Interferometer experiments by Michelson, Morley, and others at the end of the 19th and beginning of the 20th century empirically established these symmetry properties of the spatiotemporal background relative to those of the Maxwellian electromagnetic field, that is, the properties of what we now call Minkowski spacetime, in the same sense that the symmetry properties of the Maxwellian electromagnetic field were previously empirically established by Hertz. That doesn't mean like we're never going to change our mind about this. By contrast, however, appealing instead to hypothetical physical mechanisms generating contractions of rods and retardations of clocks while retaining the Newtonian spatiotemporal background structure with its planes of absolute simultaneity, which could happen, goes well beyond what can be empirically established, as far as I know, at least so far today, in the same way that Newton's opponents within the mechanical philosophy appeal to otherwise empirically undeterminable vortices in the ether to explain the motions of the planets. The crucial question for Einstein's general theory of relativity was then how to represent the gravitational field within the background structure of Minkowski spacetime, where this field must now be finitely propagated like the Maxwell field. And the solution Einstein arrived at, to put it in the briefest and almost telegraphic terms, was to retain the structure of Minkowski spacetime, and thus the light cone structure as far as possible. Here we have a wonderful picture from Gauroche's General Relativity from A to B, showing how you can translate what's going on with gravity into what's going on with the tilting and contractions of the light cones around a black hole, can be translated into a special relativistic, as it were, flat initial background. Okay. Now, the resulting four-dimensional space-time geometry here, say, around a black hole, has implications for three-dimensional purely spatial geometry. Indeed, as is well known, the three-dimensional spatial geometry of the solar system can be visualized in 2 dimensions as circularly symmetric with increasingly negative curvature, radially approaching the central sun. This is a certain model of the spatial part of the Schwarzschild geometry due to Flamm. This representation allows one to visualize Einstein's prediction of the deflection of light in the gravitational field of the sun that was tested during eclipse observations in 1919. To fully appreciate the import of these observations, however, one needs to bear in mind that the Einsteinian prediction was being tested against a corresponding Newtonian prediction, going back to the turn of the 19th century. There was always an alternative here, in which light was represented as a very small and very light, almost negligibly massive particle, moving at the already known velocity of c, of course if it's Newtonian, relative, that is, to a frame of reference centered on the sun. In particular, the Newtonian predicted deflection turned out to be 1/2 the value of Einstein's. And here, if you look at what this little box says, which is in this picture, which just shows the spatial curvature, not the space-time curvature, in parentheses, actual travel takes place in space-time rather than space. Correct deflection is twice that given by the above elementary picture. So this just raises a question in my little mind anyway, whether if we're now thinking, say, of the Newton-Cartan representation of Newtonian gravity, which presumably is empirically equivalent about this, if you can make sense of it there, for Newton's original theory, then it looks like the extra part that was missing is the additional curvature in the spatial geometry. I don't know if that's correct. Maybe it is. What do you think?
That's my feeling, but I
What do you think?
would defer to David on that.
Sure.
Yeah, but he would he'd be able to figure it out, but I couldn't. Okay. So if you get a chance, let me know. At least John Norton, without thinking too much, said, "Yeah, that's right." Thus, the observations and photographic measurements of the full Einsteinian deflection in 1919 empirically established a structural relationship between Newtonian and Einsteinian gravity, where gravity is now, for Einstein, of course, represented as a curvature imparted to him in cosmic space-time, rather than as a Newtonian impressed force, just as the previous observations and experiments of Newton, Hertz, and Michelson-Morley et al. Established the mathematical structural properties of different forms of causal interaction at issue in these cases. Again, it's provisionally established, this isn't a conclusive proof of anything, this is just one test. But it does empirically realize the difference between Newton and Einstein about this deflection, which would actually apply also, because you could have a Newtonian representation of a black hole where the light is close enough and the thing is massive enough that it would never escape once it got into that gravitational field. The continuity in method and resulting epistemic status involved in all three cases, that is Newton, Maxwell, Einstein, captures the sense in which Newtonian methodological structuralism can indeed be extended into the post-Newtonian period. Of course, the nature of the causal relation undergoes very important changes. In the Newtonian case, the relevant force, the gravitational field, mediates the interactions between material substances without being an actor in turn. The only substances, properly speaking, are, if you want to speak of substances, are massive material bodies, and they do not exchange momentum in turn with the gravitational field. This situation fundamentally changes with the electromagnetic field, which is continuously propagated with a finite velocity rather than instantaneously. It thereby exchanges both momentum and energy with the relevant charged bodies upon which it acts and is thereby acted upon. The situation changes even more radically in the general theory of relativity, where the gravitational field is not only propagated continuously, again with velocity of light, but is now a field of geometrical curvature in the fabric of space-time itself. And of course, using interferometer experiences, interferometer measurements apparently, we have now empirically realized that. And this transformation of geometry, including even the three-dimensional geometry of space, into a physically acting and interacting field of curvature, implies, for example, again, that the Kantian conception of space as the a priori form of outer intuition has most definitely broken down. Thus, the continuity in question is neither in reference, nor in ontology, nor even in conceptual structure. It rather consists, as I have said, in a continuity of structuralist methodology, that is, abstraction from hypotheses in a certain way, that was first clearly articulated by Newton and put into extensive and fruitful, very fruitful practice from Newton to Maxwell to Einstein and beyond. Thank you.